There's a fisherman in Pozzuoli, Italy, who wakes up every morning and walks to his boat. He has done this for 30 years. He knows the harbor the way you know your own kitchen. Every angle, every sound, every way the light hits the water at 6 in the morning in October. And sometime in the last few years, something changed. Not dramatically, not in a way that makes headlines. The boat sits at a slightly different angle than it used to. The dock geometry is subtly wrong. The water level relative to the stone steps he has walked down 10,000 times is not what it was. He notices. He says nothing. Because what do you say? The ground is rising, not the way ground rises in an earthquake, sharp, violent, over in seconds. This is something different. This is slow, continuous, relentless. The ground beneath Pozzuoli has been rising for 19 years without pause, without reversal, without any sign that it intends to stop. It has risen nearly 7 meters since 2005. And the rate is accelerating. Something is changing underneath this place. And in 2025, for the first time in the history of studying the system, scientists have a mathematical language precise enough to describe exactly what kind of change it is. The answer they found is not what anyone expected. It is not simply alarming. It is something harder to process than alarm. It is mathematically unprecedented, physically coherent, and honest about what it does and does not know. This is that story. Before anything else, you need to understand what Campi Flegrei actually is, because most people have the wrong picture. When people think of a volcano, they imagine a mountain. A dramatic cone rising from a plain, snow-capped, obvious, visually announcing its danger from 100 miles away. Campi Flegrei is nothing like that. There is no peak. There is no cone. There is no obvious visual threat that would make a stranger look twice. What there is instead is a caldera, a collapsed volcanic system roughly 13 kilometers across, formed not by a single eruption, but by the catastrophic implosion of its own magma chamber after a super-eruption approximately 40,000 years ago. The caldera rim now forms the hills surrounding Naples and the Phlegrean Peninsula, and the entire Bay of Pozzuoli sits inside it. This means that Campi Flegrei does not surround people from a distance. It is underneath them. The city of Pozzuoli, population 75,000, sits directly on top of the caldera's center. The city of Naples, population 3 million, lies just outside the eastern rim. When scientists talk about the population exposure for this system, the number they use is approximately 1 million people living inside the caldera hazard zone. These are not people who live near a volcano. These are people who live on one. The name translates with almost poetic precision. Campi Flegrei means the burning fields. The Romans knew. The ancient Greeks knew. Virgil described the area around Lake Avernus, a crater lake within the caldera, as the entrance to the underworld. Sulphurous vents, boiling mud pools, ground that hissed and steamed. This place has announced itself for thousands of years. And for thousands of years, people have chosen to live here anyway. The soil was extraordinarily fertile. The fishing grounds were exceptional. The thermal baths, fed by geothermal heat, were a source of wealth. The harbor was among the finest in the ancient Mediterranean. The calculation, danger weighed against abundance, kept coming out on the side of staying. The last eruption was in 1538. A new cinder cone approximately 140 meters high appeared in a matter of days, formed by an eruption that lasted roughly a week. About 24 people died. By geological standards, it was a minor event. And then nothing. For nearly 500 years, the system has inflated, deflated, rattled with earthquakes, vented sulfurous gas from the Solfatara crater, and done everything except erupt again. That long silence is part of what makes the current situation unusual. And to understand why, you need to understand what the ground has been doing. Campi Flegrei has a documented history of what scientists call bradyseism, a slow vertical movement of the ground up or down, driven by pressure, changes in the hydrothermal and volcanic system beneath. The caldera floor rises during periods of increased activity and subsides during quieter periods. This is not unusual behavior for a large volcanic hydrothermal system. What is unusual is the scale, the duration, and the character of the current episode. The major bradyseism crises of the 20th century provide the comparison points. Between 1969 and 1972, the ground rose approximately 170 centimeters. Between 1982 and 1984, it rose another 162 centimeters, intensely enough that the Italian government ordered the evacuation of roughly 40,000 people from central Pozzuoli. That evacuation, the displacement of tens of thousands of people from their homes, the partial emptying of an ancient city, happened without an eruption. The system deflated, the ground came back down, people returned. The current episode began around 2004 to 2005. Since then, the ground has risen approximately 7 meters, with no significant sustained reversal. The cumulative uplift from the current episode already exceeds either of the two 20th century crises individually. But the comparison that matters is not simply about magnitude. It is about structure. The 1969 to 1972 and 1982 to 1984 episodes were compact in time. Intensive crises lasting months to a few years, followed by deflation. They were episodic. They had clear boundaries. The system inflated, then recovered. Each crisis was serious, but each crisis was bounded. The current episode has been running for 19 years. It is not episodic. It has no visible boundary. It is not deflated. And according to a study published in 2025, the mathematics describing its behavior has changed class entirely. This is the finding that changes everything about how we understand what Campi-Flegrei is currently doing. For nearly 40 years, the dominant mathematical framework for accelerating volcanic unrest has been a model developed by Barry Voigt in 1988 and 1989. The Voigt method assumes that the rate of change in a volcanic system grows in proportion to the current state of that system, a feedback relationship that naturally produces exponential growth. If deformation is accelerating, you fit an exponential. If seismicity is climbing, you fit an exponential. It works for most systems. It has worked reliably for decades. It is the foundational language of eruption forecasting. At Campi-Flegrei, the exponential no longer fits. Researchers found that a different mathematical structure, one called a finite time singularity, describes the data with dramatically higher statistical accuracy, and the difference between exponential growth and a finite time. Singularity is not a matter of degree. It is a matter of kind. An exponential system grows proportionally. The rate of acceleration depends on the current state of the system. Double the activity, double the acceleration. It is a clean, comprehensible feedback loop that keeps compounding on itself. A finite time singularity is different at a fundamental level. It describes a system whose rate of acceleration is growing faster than its own current acceleration. The system is feeding back on itself not proportionally, but superlinearly. Each cycle of the feedback loop does not simply repeat the previous one at a higher level. It starts from a slightly more favorable condition for generating the next cycle, which means the amplification itself grows. And built into the mathematics of this structure is a defined endpoint, a moment at which the equations formally break down, at which the variables the model is tracking go formally to infinity, and at which the current regime must by mathematical necessity end. That moment, extracted from the right GPS deformation data and from the Benioff strain accumulation of regional seismicity, falls around the year 2033. The 95% confidence interval runs from 2030, 1 to 2034. 5. Now stop. Because this is where the story almost always gets distorted, and the distortion matters. 2033 is not an eruption date. The researchers are not predicting that Campi-Flegrei will erupt in 2033. The critical time, T sub c in the equations, does not forecast a specific physical event. What it identifies is the point at which the system's current dynamical behavior reaches its own inherent boundary. The mathematical regime the system is currently operating in cannot persist past approximately that horizon. Something must change. But what changes at that boundary could be an eruption, a deflation phase, a regime transition, or something scientists do not currently have a framework to describe. What it cannot be is a continuation of the present trend. The mathematics rules that out completely. This distinction between a regime boundary and an eruption forecast is not a technicality scientists use to hedge their language. It is the actual substance of the finding. Previous work on Campi-Flegrei asked how fast the system was accelerating and what that implied about eruption probability. The 2025 study asks a more fundamental question: what class of dynamical system is this? And the answer changes how we understand everything else about the situation. The statistical evidence for the singularity interpretation is not ambiguous. The inverse time linearization, the transformation that, if a singularity model is correct, converts the data into a straight line, produces an R-squared value greater than 0, 99. Across more than 2 decades of data, across multiple different time window selections chosen to verify robustness, the model fits with near perfect precision. R squared of 0. 989 does not happen by accident. It does not happen because the model is marginally better than the alternative. It happens when the model is describing something real about the system. And what makes the finding more compelling than any single R squared value is that 2 completely independent datasets converge on the same result. The first is the right GPS deformation record. The precise vertical movement of the ground at Pozzuoli, measured continuously since around the year 2000. The second is the Benioff strain accumulation from regional seismicity, a measure of the cumulative seismic energy released by the earthquakes that have been shaking the caldera with increasing frequency and intensity. These 2 datasets measure completely different physical phenomena through completely different instruments. Both fit the finite time singularity model. Both converge on the same critical window. Both point to approximately the same mathematical horizon. The probability that two independent signals, measuring different aspects of the same geological system, would independently converge on the same critical time range purely by coincidence is not something you dismiss. What the convergence tells you statistically is that whatever structure is driving the singularity behavior is embedded in the system itself, in the underlying physics, not in measurement noise or modeling assumptions. To understand what that underlying physics actually is, you need to go below the surface. Somewhere beneath the caldera floor, probably at depths between 3 and 8 kilometers, there's a body of partially molten rock. Not a lake of liquid magma, but a crystalline mush, hot and partially molten under enormous pressure, containing dissolved gases that want to escape. Carbon dioxide, water vapor, sulfur dioxide, hydrogen sulfide. These gases are held in solution by the pressure of the overlying rock column. But as the system evolves, some of those gases exsolve. They separate from the melt and begin migrating upward through the rock as a separate fluid phase. This volatile injection is the input signal. It is the starting point. The rising volatiles enter the shallow hydrothermal system, which sits above the deep magmatic reservoir at depths of roughly 1 to 3 kilometers. This system is a complex network of fractures, pore spaces, and hot water that mediates between the deep magma and the cooler, shallow crust. The influx of additional volatiles from below increases the pressure in this hydrothermal system. Hot pressurized fluid occupies more volume than cool fluid. The rock above must accommodate that volume change. It inflates. The surface rises. The right station measures the uplift, centimeter by centimeter, year by year. As the rock inflates under the accumulated stress, both the tensile stress from above and the shear stress along pre-existing fault structures, it begins to fracture. Earthquakes occur. Energy is released as seismic waves. And here's the critical detail. The fractures created by those earthquakes do not close after the event. They remain as permanent pathways in the rock. The system has been structurally altered by each earthquake that expressed its damage. Those new fractures are conduits. Hot fluid and gas can now flow through rock volumes that were previously less permeable. The network of pathways connecting the deep pressure source to the surface has expanded. More fluid can move. More pressure can be transmitted upward. More volatile gas can reach the hydrothermal system, which means more pressurization, which means more deformation, which means more inelastic damage, more fractures, more earthquakes, more permeability increase. The loop closes. Each iteration does not simply repeat the previous one. It starts from a slightly more damaged, slightly more permeable, slightly more connected rock volume. The feedback is not proportional, it is multiplicative. This is the physical engine of the finite time singularity. The mathematics is capturing in abstract form this physical loop, a self-reinforcing cycle in which each revolution creates slightly more favorable conditions for the next. There is a concept in rock mechanics that sits at the center of this story, and understanding it clarifies why the singularity model fits where the exponential does not. The concept is inelastic deformation. When rock is subjected to stress, it initially deforms elastically, meaning that if you remove the stress, the rock returns to its original shape. The deformation is temporary, recoverable, reversible. An elastic system has no memory. Its current state is fully described by its current stress level, but when stress exceeds a critical threshold, or when it is applied repeatedly over a long enough time, rock begins to deform inelastically. Microfractures form, grain boundaries shift. The internal structure of the rock accumulates irreversible changes. Inelastic deformation creates more fractures than elastic deformation produces. More fractures create more pathways for fluids. More fluid migration creates more pore pressure changes in localized zones, which triggers seismicity even in areas not currently experiencing maximum deformation. And critically, inelastic deformation means the system has memory. Its current state is not fully described by its current stress level alone. It is also shaped by the entire history of stress it has experienced. This is why the exponential model stopped working at Campi Flegrei. The exponential model assumes proportional feedback, the kind you get in a system undergoing primarily elastic deformation, where behavior is governed by current state. But Campi Flegrei has been accumulating irreversible inelastic damage for nearly 2 decades. The rock is not simply bending under the load. It is breaking, grain by grain, fracture by fracture, in a way that cannot be undone when pressure eventually changes. The feedback is not proportional to current state. It is amplified by the accumulated history of damage. The researchers identified a specific year in which this transition became mathematically unambiguous. That year is 2022. Around 2022, the Campi Flegrei system appears to have crossed from a regime of predominantly elastic deformation into a regime of predominantly inelastic deformation. The seismic character of the unrest changed. Not just more earthquakes, but a different kind. The frequency magnitude distribution shifted in ways consistent with rock fracturing under stress that exceeds elastic recovery threshold. The spatial distribution of seismicity began evolving in ways suggesting fracture propagation rather than simply stress release along pre-existing structures. And the rate of seismic energy accumulation relative to surface deformation began the faster than expected divergence that is one of the most physically meaningful anomalies in the entire dataset. Before the 2022 transition, Campi-Flegre's unrest history could be read as episodic. Inflation, partial deflation, relative calm, then new inflation. Each episode was serious, but bounded. There was a template, and the template included recovery. After the 2022 transition, the template no longer applies. The damage accumulated during previous cycles is structurally embedded in the rock. The baseline from which each new increment of stress operates is weaker than the baseline from which the previous increment operated. The system is path-dependent in a very specific physical sense. Its current state cannot be fully described without reference to everything that came before it. This has a chilling implication. Even if activity at Campi-Flegre were to slow or partially stabilize tomorrow, the system would not return to where it was in 2005. The accumulated damage is not reversible. Weakened rock does not unfracture. The system has been permanently changed by the last 19 years. Whatever happens next will happen in a structurally altered caldera that has less resistance to failure than it did when this episode began. The geochemistry at Solfatara crater tells the same story from a different direction. Solfatara is a small volcanic crater within the Campi-Flegre caldera, and it has been continuously venting sulfurous, carbon dioxide-rich steam for centuries. It is, in the most literal sense, a window into the subsurface chemistry of the system. What that window has been showing over the past decade is a shift in the ratio of hydrogen sulfide to carbon dioxide in the fumarolic emissions, a shift that carries a specific geochemical fingerprint. When the ratio of hydrogen sulfide to carbon dioxide rises, it suggests that the deep magmatic volatile contribution is increasing. More gas is arriving from depth, bypassing or overwhelming the shallow hydrothermal scrubbing that would normally remove hydrogen sulfide before it reaches the surface. This rising ratio is not definitive proof of new shallow magma intrusion, but it is consistent with and strongly suggestive of an increase in deep volatile release, the degassing of magma at depth, pushing more gas upward through the crust, through the hydrothermal system, toward the surface. Hot acidic fluids and gases, particularly sulfuric acid produced from hydrogen sulfide oxidation in the shallow system, are chemically corrosive to rock. They attack the silicate mineral structure at fracture surfaces, a process called stress corrosion. Stress corrosion weakens fracture surfaces, reduces the friction coefficient, and makes rock more susceptible to slip at progressively lower stress levels over time. This chemical weakening compounds the mechanical weakening from inelastic deformation. The rock is not just being damaged physically, it is being corroded chemically. Two separate processes, operating simultaneously, both making the system more susceptible to failure. More volatile flux means more pressure. More pressure means more seismicity. More seismicity means more fractures. More fractures mean more permeability. More permeability means more volatile flux. The loop tightens. The singularity exponent reflects this tightening. The mathematical curve grows steeper because the physical process is growing more efficient at amplifying itself. One of the most conceptually significant findings in the 2025 study involves a technique called transfer entropy analysis, a statistical method borrowed from information theory that measures the directional flow of information between two time series. It asks, does knowing the recent history of variable A help you predict the future state of variable B? And, crucially, it is directional. You can ask whether A drives B, whether B drives A, and get statistically separable answers. When researchers applied this technique to the Campi-Flegre dataset, the results were unambiguous. The causal flow from GPS deformation to seismicity is strong and statistically significant. The reverse flow, from seismicity to deformation, is weak and not statistically significant. The causal flow from the hydrogen sulfide to carbon dioxide ratio to seismic acceleration is measurable as a secondary driver. In plain terms, the seismicity is not driving the system. It is a response to the system. The earthquakes are outputs, not inputs. They are generated by the deformation and the volatile flux, not generating them. This inverts a foundational assumption in volcanic hazard monitoring. Traditional protocols, particularly for caldera systems without an obvious edifice to instrument, lean heavily on seismicity as the primary escalation signal. Earthquake swarms trigger alert level reviews. Seismic energy release rates feed into probabilistic forecasting models. The entire architecture of risk communication rests on the implicit assumption that when seismicity increases, the system is becoming more dangerous. And when seismicity is relatively quiet, you have some buffer. At Campi-Flegre, if the transfer entropy result holds, That architecture may be partially inverted. The real driver is the deformation, the continuous accelerating inflation of the caldera that reflects the pressure and volatile input from depth. Seismicity is tracking that inflation, responding to it, generated by it. This means a period of relatively lower seismicity would not necessarily indicate that the system is less dangerous if the deformation was still accelerating. The silence might simply mean the rock is deforming elastically at that moment, temporarily, reversibly, before the next cascade of fracturing begins. The hierarchy that emerges is deformation at the top, driven by pressure from depth. Volatile chemistry is a secondary driver, modulating the seismic response. Seismicity at the bottom as the observable expression of stress accommodation in the damaged rock volume. The whole structure couples together, and the coupling is tightening as the system approaches its mathematical horizon. One of the most important findings that prevents the most alarming interpretation of the singularity result is the absence of log periodic oscillations in the seismic data. Log periodic oscillations are a specific mathematical pattern that emerges in complex systems, approaching a critical transition through hierarchical fracture propagation, cascades of damage that move upward through scales from microscopic grain boundaries to fractures visible in outcrop to kilometer-scale structural failures. When a system begins failing this way, the oscillations it produces around its accelerating trend follow a pattern with a precise mathematical signature. They are the seismic fingerprint of a fracture network that is becoming self-organized, developing the spatial coherence and hierarchical connectivity needed to coordinate failure across a large volume. At Campi Flegrei, as of the data analyzed in the 2025 study, these oscillations are not present. The seismicity is accelerating, and it fits the singularity model. But the acceleration does not show the hierarchical oscillatory pattern that would indicate coordinated fracture propagation. The earthquakes are still spatially diffuse, distributed across the caldera rather than clustering along a developing failure surface. There is no connected fracture network that has achieved the spatial coherence needed to coordinate a large rupture or to create a conduit for rapid magma ascent. This distinction matters enormously. The critical horizon around 2033 is not a countdown to eruption. It is the projected end of the current regime, the point at which the dynamics as currently described must undergo some qualitative change. What change that is depends on how the system evolves between now and then. One possible trajectory is continued acceleration toward genuine synchronized criticality, the development of log periodic oscillations, fracture network connectivity, and ultimately a large-scale failure event. A second possible trajectory is deflation or regime change before the critical horizon is reached, some process arresting the feedback loop before it reaches the singularity boundary. A third possibility is a transition to a regime that current models cannot adequately describe, something that is neither eruption nor simple deflation, but a restructuring that the singularity mathematics can identify as a boundary without being able to characterize what lies on the other side. The mathematics does not specify which of these occurs. It specifies only that the current trajectory cannot continue. That is simultaneously more precise and more uncertain than a simple eruption forecast. And that combination of precision and honest uncertainty is exactly what makes this study scientifically significant rather than just alarming. There is a concept the researchers introduce called the predictability paradox, and it is one of the more counterintuitive findings in the entire paper. As the singularity system approaches its critical horizon, the mathematical precision of the forecast paradoxically decreases. The closer you get to T sub c, the less certain you can be about the exact timing and nature of the transition. This sounds wrong. Shouldn't more observations narrow down the range of possibilities? Shouldn't a longer, richer dataset allow a more precise forecast? In normal statistics, yes. In the context of a finite time singularity, no. As the system approaches the critical point, it becomes increasingly sensitive to small perturbations. The same small input, a slightly higher volatile flux, a slightly larger seismic event, a minor change in the hydrothermal system's thermal structure, produces a much larger change in the system's trajectory near the singularity than it would produce far from it. This is called sensitivity amplification, and it is a mathematical property of all singular systems. Near the singularity, tiny differences in initial conditions map to vastly different outcomes. This means that as you add more data, as you observe the system closer to T sub c, the range of possible physical outcomes actually expands rather than contracts. The researchers introduce what they call trust horizons. There's a time range over which the singularity model gives useful, reliable guidance. That range is approximately now through the late 2020s. Beyond that, as T sub c approaches, sensitivity amplification takes over, and the specific physical outcome becomes progressively harder to pin down. Knowledge and uncertainty will increase together. The practical implication of this is urgent rather than paralyzing. The window for meaningful preparation, the period when the system is still in its more predictable phase, when signals are still gradual enough to be read carefully rather than reacted to urgently, is the current one. Waiting for the picture to clarify is, in this mathematical framework, waiting for it to become simultaneously clearer in some respects and more uncertain in the ones that matter most. The 2025 study frames what to watch for with enough specificity to be operationally useful. The single most important escalation signal is the appearance of log periodic oscillations in the seismic data. Their absence now is one of the key reasons the study does not support an imminent large-scale eruption interpretation. Their appearance, when and if they emerge, will not arrive as a single dramatic signal. They will emerge gradually in the data, initially detectable only through careful statistical analysis, becoming more obvious over weeks and months. This means the signal is an early warning indicator with meaningful lead time, provided the right analysis is running on the right data in close to real time. The second key escalation signal is fracture network connectivity, whether the seismicity begins to cluster spatially along developing fracture surfaces rather than remaining scattered and diffuse across the entire caldera volume. A diffuse seismicity pattern tells you the rock is cracking throughout a large volume under generalized stress. A spatially organized pattern clustering along specific orientations and depths tells you a failure surface is developing. The third is synchronized acceleration across multiple variables, a moment at which deformation rate, seismicity rate, and geochemical signal changes all begin increasing simultaneously rather than on their partially independent trajectories. If that synchronization arrives, it would indicate the feedback loops connecting them are strengthening, and the system is moving from the accelerating but diffuse phase toward the organizing for transition phase. On the stabilization side, the most significant signal would be a sustained reversal in the hydrogen sulfide to carbon dioxide ratio at Solfatara, suggesting that the deep volatile flux driving the feedback loop is weakening. Paired with a deformation rate plateau or actual ground subsidence, these two signals together would represent the most reassuring combination of observations possible within the current monitoring framework. The monitoring infrastructure at Campi Flegrei is among the most extensive deployed on any volcanic system in the world. The INGZVO, Istituto Nazionale di Geofisica e Vulcanologia, publishes its monitoring data openly. The GPS deformation records, the seismic catalogs, the geochemical measurements from Solfatara, all publicly available. The technology to detect the signals that matter exists. The question is whether it is being used in the right analytical framework, running the right models in close to real time, watching the right variables in the right ways. The 2025 study represents exactly the kind of integrated, multivariable physics-based analysis that conventional seismicity-focused monitoring cannot fully replace. What it provides that no previous framework for Campi Flegrei has provided is a quantitative baseline precise enough that deviations from it in either direction, toward escalation or toward stabilization, are immediately meaningful. Every new data point from Wright, every new earthquake in the catalog, every new fumarole measurement from Solfatara is now a data point that can be evaluated against the predicted trajectory of the singularity model. Departures from that trajectory are detectable in real time. There is a Roman fish market called the Macellum in the harbor at Pozzuoli. Its columns still stand. If you look at them carefully, you will see the borings of marine mollusks, lithophaga, sometimes called date mussels, at heights of nearly 6 meters above the current waterline. 6 meters. Those borings are a geological record of how high the sea level was relative to this ground during an earlier submergence phase, when the caldera had deflated enough that Pozzuoli sank below the wave zone. And what followed that submergence, eventually, was the uplift that preceded the eruption of Monte Nuovo in 1538. The columns are not a tourist attraction. They are a stratigraphic record of a system that cycles, that rises and falls and rises again, and that has, at least once in documented history, risen far enough to produce a new volcano. The projected uplift at the critical horizon, based on the current rate trajectory, approaches 4 meters total. The current uplift is already 7 meters. The difference, roughly 2, 3 additional meters, is not just a number. It is a measure of how much further the system needs to be pushed to reach its mathematical boundary. In terms of coastal geography, it means the harbor at Pozzuoli will continue to transform. In terms of infrastructure, it means buildings and roads built to current elevation relationships will be operating in a geometrically different environment. In terms of rock mechanics, it represents a very large additional increment of strain in a crust that is already operating in a damaged, irreversible regime. The columns of the Macellum have stood for 2,000 years and watched the ground rise and fall and rise again. They are witnessing the fastest and most structurally unusual episode in their existence. The question this situation raises is not purely geological, it is human. What do you do with a mathematical horizon? What does it mean for emergency planning, for population management, for the daily lives of 1 million people, when the equations tell you that the system they live on is approaching the end of its current behavior? but cannot specify what that end looks like. The civil protection authorities in Italy have elevated alert levels for Campi Flegrei multiple times in recent years. Evacuation planning exists for the most exposed zones around Pozzuoli, but the 2025 study raises an implicit challenge to how that planning is being done, because it suggests the optimal window for preparation is not when the picture becomes clearer. The mathematical framework predicts that the picture will become simultaneously clearer in some ways and more uncertain in the ones that matter most as T sub C approaches. The optimal window is now, while the system is still in its more predictable phase, while the signals can still be read gradually rather than urgently, while there is still time for preparation that is careful rather than reactive. The finite time singularity is not a prophecy, it is a description. It describes a system approaching the boundary of its own current behavior, the point at which the governing equations of the present regime cease to be valid and something new must take their place. It is careful enough and rigorous enough and honest enough to say exactly this and nothing more. We know the clock is running. We do not know what it is counting down to. That combination, certainty about the existence of the boundary, genuine uncertainty about what the boundary contains, is one of the stranger epistemic positions that science can find itself in. It does not give you the narrative closure that human psychology tends to demand when the stakes are high. It does not say evacuate by this date. It does not say you are safe until that date. It says something harder and more demanding than either of those. The system you are living on is entering territory it has not occupied since 1538. The entry window is approximately now through the early 2030s. The outcome space includes several possibilities of varying severity, and exactly 0 possibilities that look like the last 19 years continuing unchanged. The ground beneath Pozzuoli is still rising. The right antenna is still measuring. The data is still arriving. The equations are still running. And somewhere beneath the Bay of Naples and rock that has been fracturing and accumulating irreversible damage for nearly 2 decades, a system is approaching the end of what it has been and the beginning of whatever comes next. The fisherman notices the angle of his boat. The old man at the cafe notices the cracks in the wall. The McKellum columns stand in the harbor with their mollusk borings 6 meters above the waterline, recording everything. The mathematics has now given us the language to understand what they have been witnessing. The only question that remains, the one the equations cannot answer, the one that falls entirely to us, is whether we have the wisdom to act on what the numbers are telling us before the numbers change in ways that leave us no room to act at all. There is one more thing worth addressing directly, because it always surfaces in conversations about Campi Flegrei, and letting it stand unanswered does a disservice to the genuine scientific story. The most common alternative narrative about this situation is suppression. The idea that Italian authorities, or some broader international scientific establishment, are concealing the true severity of the situation to prevent panic. This narrative misunderstands how volcanic monitoring in Italy actually works. The INGV publishes its monitoring data openly. The GPS deformation records, the seismic catalogs, the geochemical measurements from Solfatara, all of it is publicly available and has been used by researchers at multiple independent institutions to produce exactly the kind of analysis the 2025 study represents. The paper itself was uploaded to a public preprint server specifically designed to make research available before formal peer review. The data is not hidden. The analysis is not classified. The scientists studying the system are not coordinating a cover-up. They are publishing their findings as quickly as the research process allows, precisely because they understand the stakes involved. The second common misinterpretation is simpler and, in some ways, more dangerous, treating T sub C as a deterministic eruption date. The sentence, "Scientists say Campi Flegrei will erupt in 2033, is easy to write and completely wrong in every important way. The singularity is a regime boundary, not an eruption forecast.